Rennovia. Just a few more words on Gary. Gary joined Rennovia back in 2010 to lead the product development and commercialization effort. Before that, Gary was Vice President at Cimix Technologies for catalysis. And Gary has a very extensive career. He has 49 issued U.S. patents ranging from novel catalyst and materials to high throughput screening technology. So please help me welcome Gary Diamond.
Okay, thank you, James, for the very kind introduction there. So today I'm going to talk to you about Rennovia's scale-up and commercialization strategy for our first announced product, which is bio-based adipic acid. And first, a very quick introduction to Rennovia. We are a relatively new company. We're about 2.5 years old now, so we're just starting to walk and make a lot of noise. We are backed by venture capital. We're based in Silicon Valley. The founders of the company and myself and many of the scientific staff actually come from a previous Silicon Valley company called Cimix Technologies, where we developed high throughput catalyst and materials synthesis and screening technologies. We are using those technologies as our kind of bedrock for renewable chemicals development. But we have also very deliberately hired a very experienced team of chemical industry veterans from companies like Ventura, DuPont, BP, BASF, and ExxonMobil. We have very deliberately created this mix of Silicon Valley R&D types and people with a lot of experience in the chemical industry, people who have built plants and run chemical businesses, and we see that as being a very important combination. So our mission, we're in Silicon Valley, so we have to have a mission statement. Our mission is to develop catalytic chemical processes as opposed to biological processes for producing existing major market chemicals. So we are going exclusively for drop-in chemicals that already have large markets, typically multi-billion-dollar markets, but changing the raw materials to renewable bio-based feedstocks. Our focus, as our CEO likes to say, is on cost, cost, and cost. And I think that message has come across this morning already, that it's nice to be green, but nobody wants to pay for it. So really the only sustainable advantage that you're going to have over the years is cost. For us, that's the cost versus the incumbent petroleum-based processes. And thirdly, we are not a one-product company. We have a pipeline of products that are not yet announced, but that are going through our development and scale-up process. So this is the breakdown of a typical barrel of oil in the US, either produced locally or imported. About 70% of a barrel of oil goes to transportation fuels. Only about 3.5% goes to chemicals, and yet the value created in the petrochemicals industry is almost the same as that created in the transportation fuels. So the volumes are a lot lower than fuels, and that becomes important, particularly around feedstock and food versus fuel issues, etc. But the value created in the chemical industry really is huge. This is the financial underpinnings for our company and for many other companies here. You know, the rise in oil price gets people's attention when they're at the pump, but the key petrochemical petrochemical feedstocks have really trapped oil, or in some cases have the prices have risen even faster. Butadiene is a nice case there because of changes in technology for the cracker feeds, etc. So compared to oil and also the key petrochemical feedstocks, we show a US starch here. This is from corn, and over the last decade has seen about 1/5 the price rise and about 1/5 the price volatility, which is also critical. There is now an industry-wide recognition of the need to diversify raw material supply. So our strategy really is to intersect the existing petrochemical value chain, and in order to do this in a cost-competitive nature, we do not try to intersect at the first level the kind of super commodities, the basic refinery chemicals like ethylene, propylene, benzene, etc. Those are very difficult to produce competitively from renewable resources today, even at today's oil price. However, we've identified that chemicals that are 1 or 2 steps further on can offer some very good candidates for cost-competitive production from renewable feedstocks. And typically, as you get further from the refinery, the chemicals actually become more functionalized, and so we get to utilize more of the functionality that's inherent in our case, carbohydrates. So this is probably heresy for this meeting, but we strongly believe that a bio-based chemical industry does not necessarily imply a reliance on industrial biotechnology and fermentation. Yes, sorry. I'll have to go to confession afterwards, I think. We do recognise that, for some targets, such as lactic acid, for example, fermentation is the obvious answer. There are many chemicals that bugs and yeast love to produce. However, many of today's petrochemicals, if you're going to make drop-in bio-based replacements, they don't look much at all like the kind of things that bugs and yeast like to produce. We see chemical catalysis as providing a real alternative, and we believe in some cases a much better alternative for the efficient production of bio-based chemicals. This is an area where the US has typically been one of the global leaders, along with countries like Germany and France. I should probably list them all. I'll start upsetting the Netherlands, obviously. Yes. Okay. Catalysts are today used to create about $2,500 billion worth of value, which is an unbelievable amount. About 90% of chemical processes use chemical catalysis. And that's where our expertise is, and we see this as being a very promising strategy. So in terms of feedstocks, this has already been touched on before, and I think our feedstock strategy, I think, is very much in line with the strategy that AkzoNobel are following. We intend to use existing carbohydrate feedstocks that are available in multi-billion pound a year scales today as a first generation. There, we're focusing, in the US on corn, and we're, competing, if anything, with high fructose corn syrup, which consumers are turning away from, and there's actually been a pretty strong decline in the production of over the last, in the production for the US over the last few years. So we see that as being a good strategy, and one that the corn wet millers are interested in finding alternative uses for the glucose that goes into high fructose corn syrup. But going forward, we intend to be fully compatible with the emerging lignocellulosic technologies. As I say, in the short term, we will be using corn, but because of the couple of orders of magnitude difference in scale, the issues versus fuels are much less. Okay, so our first announced product is bio-based adipic acid. There is strong chemical industry interest, as I've outlined before, and as the other speakers have. Adipic acid is particularly interesting because it's half of the raw material from nylon 6,6, which is a particularly good engineering plastic for automotive applications. It's one of the few engineering plastics that can be used under the hood because of its very good heat properties, and also, as the speakers have already described, polyurethanes also is a very large growing market. It is also, as I'll show later, an excellent target from a cost basis. So here we compare the dominant petrochemical process, which is via cyclohexane. So you start with benzene, one of these super commodities. It's reduced to cyclohexane through hydrogenation, oxidized to this Ka oil, a mixture of cyclohexanol and cyclohexanone. And then the last step is a rather nasty stoichiometric oxidation of nitric acid. And this is contributes significantly to the carbon footprint. Nitrous oxide byproduct has a very high global warming potential, as I'll get to later. In comparison, our process is just two steps from glucose, selective catalytic oxidation and a selective catalytic reduction, and our byproduct is water. So the markets have already been described for adipic acid by the other speakers, but I should point out that the intermediate, the product of oxidizing the glucose before it's reduced to adipic acid, is glucuric acid. This is actually comes under the new rather than drop-in chemicals, but there's been actually quite a lot of work over the years looking at glucuric acid as an alternative to citric acid and other organic acids. And there's some very large potential applications in detergents and also in admixtures for cement and concrete, etc. And we can also produce gluconic acid extremely efficiently as well. So where are we now in terms of development? So we've gone through the high throughput R&D, which is our kind of front end, where we're doing hundreds and thousands of experiments simultaneously. We've taken the adipic acid through our continuous reactors, and we're now at the pilot scale, and we're running at about £1 an hour in continuous reactors. We've got thousands of hours of time on stream on multiple catalyst systems, and we are now designing the next stage, which is a commercial demonstration unit, and we're looking at a ton per day scale now. And then the next stage is commercial plants. So this is some LC data. This is adipic acid. This is true adipic acid from our pilot reactor, and this is what it looks like after a single recrystallization. It's really very clean, as you can see. And this is produced. This is on the multi-kilo scale. So we have built very detailed engineering models comparing Rennovia's bio-based process with the dominant cyclohexane petroleum-based process, and those models show really significant reductions in costs, both capital costs and also operating expenses, including lower raw materials, utilities, and manufacturing costs. And this comparison is actually well below today's oil price. And today's oil price advantages even more. We have also built models of the fermentation.